After watching this video lecture, students will be able to identify the hybridization of orbitals based on observed bonding in Lewis structures. And students will also be able to draw hybridized orbitals and use the orientations of the hybridized orbitals to explain the specific bonding observed in the molecule. So the localized electron model basically analyzes bonds by looking at the orbital overlap of atoms within a bonded molecule. So in this case, what we see is that electrons that are valence electrons that are in the orbitals of these two 1s orbitals for these hydrogen atoms, they basically come in close proximity, overlap, share their electrons, and basically are held together by the interaction between the nucleus of one atom's attraction to the electrons of another, and the same being true for the other atom's nuclear attraction to the valence electron of the other atom. And basically this does a pretty good job of predicting the bonding that we would anticipate when we look at our Lewis structures. We're able to kind of think about them in a very simplistic way when we're looking at a molecule like H2 or even HCl, where you have a p orbital that contains an electron able to overlap directly with a 1s orbital, or say two p orbitals coming together. This works very well with those types of models. So simple overlaps allow this localized electron model to hold true. However, when we get into more complicated molecules, this starts to fall apart rather rapidly. And the problem is that we cannot get this localized approach to orbital overlap to match with the molecular geometry predicted by VSEPR theory. So basically another model has been established in order to explain the molecular geometries that we predict based on VSEPR. Another reason we know that the atomic orbital or that localized electron model doesn't work is because if we look at an example that's more complicated, such as CH4, we would expect the covalent bonding to occur between all the orbitals that are containing valence electrons. And in carbon's case, we have two s orbitals and two p orbitals that have electrons in their valence shell, and then we have the hydrogen atoms that have electrons in their 1s shell. So from this perspective, the combination of the 2s and the 1s and the 2p and the 1s would give us different types of bonding. However, the reality of it is that all of the bonds in the CH4 molecule are all equivalent. So once again, this localized method doesn't work, which has led us into another model for bonding. So in order to process this or think it through in a way that would make sense to us, instead of having individualized or localized orbital approaches, what we look at is, instead of having individual 2s's and 2p's, what we assume has occurred is basically a mixture of the 2s and the 2p orbitals. And this process is called hybridization. So in this mixing process, instead of having a 2s orbital and three 2p orbitals, okay, instead of having individual orbitals, what we end up with is four new orbitals called sp3 orbitals. And these sp3 orbitals are a mixture or a hybridized form of the 2s and 2p orbitals that exist on that carbon atom. So if we want to visualize this process, notice we have our 2s and then our three 2p's that are on that carbon central atom and contain valence electrons. When these four orbitals are mixed, we end up with four sp3 hybridized orbitals. And as you can see, their shape is somewhere in between the two different types of orbitals that are mixed. And subsequently, we get orbitals that are able to be oriented around that central atom in a way that will give us the bonding that we anticipate. So if we look at this, we know that our atomic orbitals are directionally oriented, okay, at least when it comes to the p, x, y, and z orbitals. Remember that they all are 90 degrees from one another. And that basically doesn't really lend us an opportunity to have a different type of bond angle or anything unique like we see in actual molecular models. So this hybridization process of these atomic orbitals gives us these sp3 orbitals. And as you can notice here, they all are able to be distributed into a different quadrant of that tetrahedrally organized shape. Okay, and if we look at them when they're all combined, we get that tetrahedral organization, and we subsequently get that 109.5 degree bond angle, or in this case, orbital relationship angle. So these orbitals, when we take them, we're going to mix our atomic orbitals, and that will give us our hybridized orbital setup. Now, in terms of energy, notice, normally our 2s and our 2p are relatively different in energy values. However, when we hybridize them and mix them, basically it causes degeneracy within the orbitals. And this is supported by the types of bonds that we see created within the molecules that are used or that are created with these types of orbital overlaps. We actually see in a CH4 molecule, right, we only see a single peak for the CH bond. We don't see multiple different ones because we're not seeing any energy differences in terms of these bonds. Each one of them is equivalent or degenerate. So when we mix these orbitals, we get when we mix these, two single 2s and 3 2p orbitals, we get 4 sp3 hybridized orbitals that are all degenerate. So identifying sp3 hybridizations, okay, so anything with a tetrahedral electron geometry, so anything with 4 electron domains around the central atom is going to be a sp3 hybridized molecule. Okay, so it doesn't have to be tetrahedral in shape, it just has to be tetrahedral in terms of electron geometry. So that means that it has 4 different groups around that central atom. Okay, so it doesn't matter if your molecule is bent or trigonal pyramidal, it should be pyramidal, in shape. In those situations, 1 or 2 of your sp3 orbitals is actually going to hold a lone pair. Basically, the electron geometry for sp3 hybridized orbitals, there has to be those 4 groups, those 4 electron domains around that central atom, and that's going to be what helps you identify it as an sp3 hybridized atom. Okay, so in this case, the oxygen atom, the nitrogen atom here, okay, in the case of CH4, the carbon, those are all, each of those atoms are all sp3 hybridized. Their orbitals have been mixed and subsequently bonded with another atom's orbitals. So now that we understand sp3 hybridization, let's go ahead and let's look at sp2 hybridization. So in sp2 hybridized atoms, basically we're taking only 3 of the unhybridized orbitals on that central atom, okay, and mixing them to give us sp2 hybridized orbitals. Okay, so in this case, when we're creating sp2 hybrid orbitals, we're taking an s orbital and 2 p orbitals. An s orbital and 2 p orbitals are mixed, so 3 atomic orbitals are used, and we get 3 hybrid orbitals. Okay, we see them below, sp2, sp2, sp2. Okay, so during this process, anytime we're looking at hybridization, the number of atomic orbitals that we mix are going to be equal to the number of hybrid orbitals that we get out. Okay, so in this case, sp2 hybridized, I've taken 1 s and 2 p's. Okay, I've mixed them together to give me 3 sp2 hybridized orbitals. Okay, so when we take those atomic orbitals, we mix them and get our hybridized orbitals. Those 3 hybridized orbitals are obviously going to orient as far away from one another as they possibly can. So in this situation, they're basically going to orient in this triangulated kind of setup, in this trigonal planar type of shape. And so this is going to help dictate a lot of the shapes that we see or have seen from our VSEPR theory predictions. Now, looking at that central atom that we're actually taking those orbitals from and hybridizing, remember it has its s orbitals and its 3 p orbitals. However, we're only taking 2 of the p orbitals and that 1 s to create the sp3 hybridized orbital. Okay, so in that situation, The 3 orbitals that we hybridized give us a degenerate set of sp2 hybridized orbitals. However, please recall that one of the p's did not get mixed. Okay, so it remains at its energetic state, okay, which is going to be slightly higher than the sp2 hybridized orbitals from the set that we observed. So when do we identify a molecule as having sp2 hybridization? Okay, so once again, we're looking at electron geometry, so we're looking at the number of electron domains around that central atom. Okay, if we have trigonal planar electron geometry, we will have sp2 hybridization occurring. Okay, so basically, anytime you have that central atom, and you only have 3 groups around that central atom, that's going to be trigonal planar electron geometry, and you're subsequently going to have sp2 hybridization. So if we look at the example that was provided right here, okay, we actually have this molecule, right, ethene, okay, and if we look at ethene, and we pick a central atom, so if I select one of these carbons and look at its central atom, okay, this carbon is attached to 1 hydrogen, 2 hydrogens, and 1 carbon. Okay, so there are 3 different electronic domains around that central atom, so it has a trigonal planar electron geometry. So that implies that it's sp2 hybridized. Okay, so in this situation, we're going to have a trigonal planar molecule, and this is my sp2 hybridized orbital set. Now, okay, the question needs to be like, well, what's happening to the p orbital that's remaining, right? I have these 3 sp2 hybridized orbitals hanging out, you know, kind of in that axial position. What is this p orbital being used for? And we're going to discuss that. So on the last slide, the question was, you know, what's going on with this p orbital that supposedly isn't involved in bonding? Okay, well, the reality of it is that this p orbital is very much so involved in the bonding in the molecule we just looked at. So if we go back to this ethene example, okay, all right, and let's say that this is a single carbon atom. So we're only looking at basically 1/2 of this molecule, okay? Now, these green ones are my sp2 hybridized orbitals, okay, and this grayish one is that p orbital that didn't get hybridized. So in this situation, when bonding is occurring, okay, the hydrogen atoms that we see here, okay, their s orbitals are overlapping in a head-on way with those sp2 hybridized orbitals. So these 1s orbitals, okay, are overlapping directly. They're actually touching each other and forming a bond. Okay, in that same way, this sp2 hybridized orbital is interacting with another sp2 hybridized orbital from the carbon that's on the right-hand side. Okay, so we have this bonding that's occurring in a very head-on, direct way. Okay. However, there is also another type of bonding that's occurring that's actually creating this double bond, and that involves this unhybridized p orbital. So we're going to look at the details of these different types of bondings, what they're called, etc. on this next slide. So this right here is a bird's eye view of what we were just discussing. Okay, so we have our sp2 hybridized orbitals on one carbon and on another carbon. Okay, and all of these sp2 hybridized orbitals are interacting with either another sp2 hybridized orbital or a 1s orbital from the hydrogen that it's bonded to. Okay, so this is really representing kind of a molecular framework like you see here. Okay, so these are the bonds that are being represented by this diagram here. Okay, now these bonds are all called sigma bonds, right? And they're sigma bonds because the orbitals are overlapping by basically touching each other, by overlapping in a head-on-head directional type of way. So the orbitals are actually overlapping with one another. Okay, so all single bonds, okay, are going to be sigma bonds. Okay, so this head-on overlap is caused by sigma bonding. Okay, now we know that this molecule is actually structurally containing a double bond, right? Okay. Well, part of that double bond is caused by that initial sigma overlap, okay? This overlap that we see right here between these two carbon atoms. However, on each carbon atom, we also have two unhybridized p orbitals, right? They're hanging out on that central atom. Okay, so because they're hanging out on that central atom, the electron density that's present there is able to overlap in a non-head-on way. Basically, it's overlap that's occurring across the distance. Okay, so double bonds or triple bonds, right? Okay, those are going to be caused by the overlap or the side-by-side sharing of electron between p orbitals. Okay, so that unhybridized p orbital is going to be very important in the formation of double and triple bonds. And we're going to discuss triple bonds in a little bit more detail a little bit later. For now, if we go ahead and take a look at the model that we've been discussing, okay, this ethylene example, okay, we've been looking at it on every slide, okay. This initial diagram allows us to see the overlap, the initial sigma bond that's formed between the sp2 hybridized orbitals on the carbon. Okay, and then this diagram right here allows us to see the pi bond formation between the two unhybridized p orbitals that exist on that carbon atom. Okay, so the overlap here is through a distance or through space. This is your pi bond, this is your sigma bond. Okay, and in this situation, if we add the hydrogens are going to come and overlap with their 1s orbitals along the other sp2 hybridized orbitals that aren't involved in carbon-carbon bonding. Okay, so hopefully you can visualize the different types of bonds that are occurring here and how these unhybridized p orbitals lead to pi bonding. Okay, so just as a review, sigma bonds, they form when orbitals basically are pointing towards each other and overlap. Okay, so you're going to have a head-on interaction. In the case of pi bonds, you're going to have parallel orbitals, and they don't actually physically overlap, but electron density is shared between them over space. Okay, so sigma bonds are always going to be single bonds are always going to be sigma bonds. Double bonds are going to have one sigma bond and one pi. Okay, and triple bonds have one sigma and two pi. And we'll talk about triple bonds here in a little bit. So here's another view. Instead of a kind of bird's eye view, now we're kind of looking at the side of the molecule. Hopefully it'll give you a better idea of how that pi bonding is occurring. Okay, so if that sigma bond between the sp2 hybridized orbital is in the plane of this nice little square here, the pi bond is going to be occurring across the space above the carbon-carbon sigma bond. So remember, this is your sigma, this is your pi. Because this is a double bond, right, you have one sigma and one pi. So if we go ahead and we look at identifying single and double and triple bonds and basically how many sigma and pi bonds are present in a specific molecule, what you're going to do is basically look at the types of bonds you have present and subsequently make decisions. But before you do that, remember that a single bond is always just a single sigma bond. Okay, a double bond has a sigma and a pi, and a triple bond is going to have one sigma and two pi bonds. So all bonding is going to start out with a single sigma bond, and if it's a double or triple, you just keep adding a pi bond to get that. Okay, so if we look at vinegar, okay, or acetic acid, and we want to identify how many sigma and pi bonds you have, first thing you can do is count up how many single bonds you have. So 1, 2, 3, 4, right, 5, 6. I have 6 sigma bonds coming from all the single bonds, right? And then I have this double bond here. Now remember, a double bond consists of a sigma plus a pi bond. So in terms of the total number of sigma bonds, I have 6 coming from all my single bonds, 1 coming from my double bond to give me 7 sigma bonds. Now, because I have a double bond consists of 1 sigma and 1 pi. So since I'm counting up pi bonds, I have a single pi bond because I have a single double bond. Okay, so that's how you would go about identifying how many sigma and pi bonds you have. It's pretty straightforward. So let's go ahead and let's talk about our last set of hybrid orbitals. In this case, we're talking about sp hybrid orbitals. So in this case, we're only hybridizing one s and one p orbital. Okay, so we take two atomic orbitals and we get two hybrid orbitals. Notice how they're oriented basically 180 degrees from one another. Okay, if we have mixed our S and our P to get two hybrid orbitals, that also means that we have unhybridized orbitals, just like we saw in the sp2 example. So if we look at their energetics, okay, remember we have our S's and our three P's. We only mixed one S and one P, so that gives us two sp hybridized orbitals, and so that means we have two unhybridized P orbitals. And that's going to come into effect and come into importance when we start looking at our bonding, just like we did before. So in the case of another carbon example here, where we have an sp hybridized carbon, in this case we're going to have the two sp hybridized orbitals, okay, and then we're going to have the two sets of unhybridized orbitals. And notice that they are 90 degrees from each other. They sit nice and comfortably around that central atom in their normal positions before hybridization. Okay, so if I took another carbon that had the same hybridization, their sp hybridized orbitals would overlap, giving us our initial sigma bond. Now, what needs to be considered, though, is that we have two unhybridized p orbital sets. Okay, so that means that we have the potential of having two pi bonds. Okay, so if we end up with two pi bonds on these two hydrogens, that means that we have a triple bond. Okay, and if we throw our hydrogens in, as we see here, okay, we're going to end up with basically this structure here, which is acetylene. Okay, so in this situation, okay, you have a sigma bond that's created by the overlap here. Okay, so that's your sigma, right? Okay, and then we have our pi bonds coming from the overlap of the p orbitals. So you see it here and here. Okay, and this is a pi and this is a pi bond. Okay, so we have two pi's and one sigma, okay, which is a representative form of what we would anticipate with a triple bond. So identifying sp hybridization, okay, so anything pretty much with linear electron geometries are going to have sp hybridization. Okay, carbon dioxide would be a great example here, right? If we look at that, okay, notice this carbon is experiencing two different double bonds. Okay, so one of these double bonds on this side is being caused by one set of p orbitals overlapping. Okay, and this one over here is being caused by another orbital overlapping. So we have our pi bonds, we have our sigma bonds, as we would anticipate. Okay, so sp hybridization is going to be associated with linear geometry, and basically that sp hybridization is going to usually be accompanied by triple bonds or multiple sets of double bonds. So what's an easy way to predict the hybridization on your central atom? Basically, you first want to draw the Lewis structure of your molecule. Obviously, this is a cornerstone of being able to identify the things we're discussing here. And then you look at that central atom and you count the number of lone pairs and the number of bonds that are on the central atom. So basically, your number of electron domains or your number of groups around that central atom. Okay, and depending on what you have is going to identify, your type of bond hybridization. So if your lone pairs plus the number of bonds is 2, you're going to have your sp hybridization. Okay, if it's 3, you have that sp2. Okay, if it's 4, you have your sp3, and so on and so forth. Okay, the 5 groups, it's sp3d. So then that's when we start getting into our trigonal pyramidal type shapes. Okay, and then 6 groups around the central atom. That's going to lead to our octahedral shape. Okay, notice in this case, these two cases, we are actually starting to hybridize in d orbitals, and basically gives us our unique shapes. So we can look at this with a little bit better diagram set. Okay, so BeCl2, that was the example we were looking at. Basically, we have 2 groups around that central atom. Both of them are bonding. Okay, we know we're going to have that linear shape based on VSEPR, but in this case, because we only have two groups around, we're going to have SP hybridization because we're mixing that S and P in order to create our two bonding orbitals. Okay, in terms of SP2 hybridized, we've mixed two P's and one S. In the case of BF3, right, we're going to have 1, 2, 3 hybridized sp2 orbitals. Remember that unhybridized p orbital still remains, but that gives us our shape and the potential for double bonding and a few other features. Okay, when we mix those 3 p's and 1 s, that gives us our sp3 hybridized orbital set. Okay, we're going to have 4 groups around that central atom, and basically those 4 groups around that central atom is what brings us into our sp3 model. Okay, same thing, when there's 5 groups around that central atom, that means we've needed to mix 3 p's, an s, and a d. And so this leads us to our trigonal bipyramidal shape. Okay, and same thing can be true for the octahedral set. So notice, we're mixing these orbitals, they give us specific hybridized sets of orbitals, which leads to the specific bonding that we see. Okay, notice when we have unhybridized orbitals, that's when the double bonding and triple bonding can usually show up. And we see those and hopefully understand those by now. So if we look at this example here, okay, and they ask us to describe the bonding in the molecule, okay, we can look at it from multiple perspectives. We could say that this carbon atom is sp2 hybridized. The reason why I know it's sp2 hybridized is because the carbon has 1, 2, 3 groups around the central atom. Okay, I can look at this carbon as having 1, 2, 3 sigma bonds and a single pi. Okay, so basically there's lots of different looks at it, but you should be able to indicate the hybridization on the central atom, should be able to identify the types and location of each bond present, and you should be comfortable obviously with drawing the Lewis structure so that you can actually make this analysis.